All right. Thank you everyone for coming and to listen to this talk. My name is Suneet, and I'm here today to talk about faster and cheaper ingestion and how we achieve that using Druid and Kubernetes. Before we dive in, this is just an overview of what we're going to talk about today. I'm going to spend a little bit of time talking about the background of why we were looking at trying to get faster and cheaper ingestion. As you can imagine, faster and cheaper are both good things, so it's probably not a lot of reason needed there. We'll talk about how we use middle manager-based autoscaling and some of the challenges we ran into when looking at that. And then we'll talk about how we move towards Kubernetes-based ingestion and how it solves those problems. We'll also do a little demo so you can see Kubernetes spin up jobs and pods and see it all working. It's very exciting. And end with some tips for how you can set this up for yourself and future work that would make this feature in Druid even more powerful. A little bit about us. My name is Suneet. I'm going to be presenting today along with George. We are both active committers on the Apache Druid project. We work on the data engineering team here at Imply. And our focus is to make Imply Polaris the cheapest and most reliable way for anyone to run Apache Druid. Now, you're probably wondering, what is Imply Polaris? Imply Polaris is a database as a service. Some of its key features is that it can deploy in seconds, it scales effortlessly, and doesn't require any Druid expertise. One of our key focuses here is we want to allow people to just pay for the ingestion that they use in the feature we call pay-as-you-go ingestion pricing. It's probably most easily explained with an example, so I'll dig in a little here. So let's say you had a batch job that you wanted to load, say, 10 gigabytes of data from S3. It requires some compute to store it in Druid, so you pay some amount of money to do that processing. If someone else wanted to load a terabyte of data, that requires a lot more processing, and so it will cost more, and that the cost is proportional to the size of the work you're doing. This is relatively straightforward for batch ingestion. I think most people can wrap their heads around this. But we'll dig into what it looks like with something like streaming ingestion with Kafka. So with streaming ingestion, the amount of data you're reading changes hour by hour. It's typical to have peaks and troughs during like high load times and low load times. And so how do you think about ingestion pricing and costing at that point? One way you could go about it is you say, hey, what's the average of my throughput? And say, that's the amount of compute resources I need to load the stream. That could work, but you have this problem where over here we have these high throughput times where you are using less resources than is needed to keep up with the stream, so your data is not up to date. And then over here you have these low throughput times where you're paying for more than you really need to keep up with the stream. So it's not really ideal. And what our customers expect is to be able to grow the compute resources based on the amount of data they have. So at low throughput times, you spend less on ingestion. And when your usage is really high, you spend more. And this thing dynamically follows the load pattern on the stream. And so what this really tells us is that what we need is the ability to do autoscaling ingestion infrastructure that is both responsive and cheap to run. And it's not just the Druid services that we need, but also the underlying infrastructure to keep up with that. To achieve this, we leaned into running Druid on Kubernetes. This is a simplified diagram of all of Druid running on Kubernetes. Some things may not run on Kubernetes in this diagram, but besides the point. What we will focus on this talk is this part of the architecture diagram here of how the ingest services run on Kubernetes. and how we will make these scale so that they can keep up with the ingestion throughput. So the first solution we looked at is middle manager-based autoscaling. As far as I know, it's available in every version of Apache Druid using this thing called a pending task-based worker provisioning strategy. It's a lot of words. We'll talk through how that works now and then show you how it looks like in real life. So if you needed to scale up, the Druid autoscaler checks if the cluster has enough ingest capacity, and it does this on some timer. If it decides that there are too many pending tasks, may ask Druid to request for more middle manager pods. Since Druid itself can't scale up the infrastructure, it reaches out to Kubernetes and asks Kubernetes to schedule a pod or to create a pod. The next thing then Kubernetes will do is look if there's enough capacity in the cluster for the pod to be created. And if not, it'll provision a node so that you can even scale up the underlying instances. Once the node is provisioned, the middle manager pod is created, and now you can run your ingestion on Druid. So this whole process is what we call like a two-phase scale up. There's scaling in Druid, and then there's scaling in Kubernetes. As you can see from the flowchart, there's a lot of points here, so it's quite complicated. On the scale down side, it's very similar. The Druid autoscaler checks if there are any idle middle managers. So it's checking every period if there's any idle middle managers. If it notices that some idle middle managers have been sitting around for too long, they get terminated. And to terminate it, Druid makes a request out to Kubernetes to terminate the pods. Once the pods are terminated, if the node has no other pods running on it, the node is deprovisioned, and that reduces our infrastructure costs. But it also makes, when the pod is terminated, there's more capacity available on the Kubernetes cluster to run other pods. So what does this look like? So this system works and is quite useful. If you look at this is middle manager-based autoscaling working in real life. This is a metric we took from when we were doing some of this testing. What you'll see is, for the most part, we're sitting around 4 or 5 middle managers, scales up or down based on need. And then there are these peaks where we jump up to like 12 middle managers and then come back down to 4, which is our normal capacity. And it's able to scale up regardless of like the workload. So like one time it scales to 12, another to 34, 35. So it's really impressive to see how Druid can talk to Kubernetes to schedule more middle manager pods to get this working. And this system worked pretty well. And then what we did was we decided we wanted to look more closely to see, are there any inefficiencies in this system? And that's when we started double clicking into this. So the first problem we noticed, if you just look at this diagram, scale up and scale down time itself can take quite a while. So if you look over here, you'll see there are little plateaus during each scale up. And that is where Druid is checking to see if any of the running middle managers free up capacity so it doesn't need to scale up again. So if you ran an ingestion job, there's little plateaus where we wait to see if we don't need to scale up more quickly. And so what that means is if you're running a really large batch job, you end up waiting a long time for all the resources to be ready to be able to run your batch job. Similarly, if you look on the scale down side, you'll see plateaus. And those plateaus are, say, Druid checking if any new work is going to be scheduled on the middle manager pod, so it doesn't need to keep thrashing, scaling up and down middle managers. So those little plateaus are some inefficiencies we need to deal with. Another issue is the diagram earlier showed it can take quite a while for a middle manager to come up, and Druid is continuously checking to try and assign pods. So you have this race condition where it's possible that a middle manager is created, and is never used. So look at this example here. We have a node with 4 middle managers, each running 4 peons, and all of them are active doing some ingestion. So if I try to like schedule a new task right now, there's no capacity on the cluster, and Kubernetes will spin up a new node. And while Kubernetes is spinning up the new node, what happens is 3 of the tasks complete. And so now the existing middle managers have 3 task slots that they can use. So when Druid sees this, it says, oh, I don't need to wait for the new node. Let me schedule the new task that you asked me onto this one. And so now this node has come up and there's no work that's going to be assigned to it. So it's going to come up and wait, be idle, and fall back down. And so that's another inefficiency in the scaling. The other problem we have is long-running middle managers. Again, best explained with an example. So let's say we're running some ingestion, and at steady state, we need 2 middle managers to run. 2 middle managers fit comfortably on a node. There's a surge of ingestion that means we need 8 middle managers to run, which takes 2 nodes. Once that surge dies, so that surge could be like a large batch job that's running. Once the batch job completes, those middle managers that were running the batch tasks are now killed or no longer running, and they get scaled down. But the middle managers with active tasks are assigned to 2 nodes. So even though we could fit 2 middle managers on 1 node, we end up paying the infrastructure cost for 2 nodes. And that results in very idle nodes and is not very efficient. The challenge here is that middle managers are meant to live and get work assigned to them. So as long as like work is being assigned, they're going to keep staying up. The other thing we've looked at is that, as this diagram shows, Druid and Kubernetes will schedule the resources needed for an entire middle manager. So if you just need 1 peon to run, we'll still ask Kubernetes to reserve the resources for all the peons on that middle manager in case future work is assigned. And so that leads to idle time on Druid, and also less efficient use of compute resources on the nodes. So I'll say all these problems are solvable. They're all solvable problems with this architecture, but it requires like fine-tuning and balancing trade-offs. And Polaris is meant to support a lot of different use cases, from people who are doing micro batch ingestion, running a batch job for 5 files every 10 minutes, to nightly ETL pipelines that like require a lot of resources to run, to streaming throughput ingestion with variable loads. So making these trade-offs is hard for an operator without deep context in the specific use case. One of the challenges we talked about is how do you avoid scaling thrashing? So we could have the middle managers be scheduled more aggressively, but they'd end up like coming up and down, and we'll have to deal with that problem. And how do you balance that with like the idea behind a middle manager is to make sure there's enough capacity to accept work at any point in time. So what is an appropriate amount of idle capacity on the cluster will be dependent on your use case. And then to solve the problem with 2 nodes, you need the ability to drain a middle manager from 1 node to the other. And all of this, again, like I said, is solvable. But when I think about it and talk about it, it makes me feel like this. You know, you're kind of trying to use whatever tool you can, try and patch it together to make it work. So this is where we decided to like look at other ways to solve this, which we're going to talk about next. It's called Kubernetes-based task scheduling. And I'm going to hand it over to George to dive into this.
All right. Yeah. Hey, guys, I'm George. I'm going to go over our solution for some of the problems we discovered with autoscaling, and then just do a quick demo. Right. So to clarify one point, I think Sunit mentioned how middle managers actually run ingestion tasks is they spawn peons, which are separate Java processes in their own container, and each peon runs its own task. So the concept behind Kubernetes-based task scheduling is to remove the middle manager entirely from the task scheduling system and to just let Kubernetes, which is a task scheduling, task orchestration system, handle the scheduling of the peons directly. So I didn't write this extension originally, neither did Sunit. It was actually a contrib extension from the community. It was originally authored by Churro Morales. I don't know his real name or her real name. So now how does this work? So essentially what happens is when a task is submitted, it gets submitted directly to Kubernetes. So Druid itself, the overlord, will schedule a Kubernetes job. And Kubernetes will then try to schedule a pod for that job. If there are not enough node resources for the pod to be scheduled, it'll schedule a node to be scaled up the same as in the middle manager system. And then once the node is provisioned, the pod can be scheduled and start running the task immediately. So essentially, we're removing the middle layer of middle manager auto scaling here. There's only one layer of auto scaling, and that's Kubernetes. And scale down is also quite similar. So your task completes, your pod exits, and if the Kubernetes autoscaler can scale down the node, then it'll scale down the node and capacity is freed up. You're no longer paying for the node. So you can see here, the system is a lot more aggressive at autoscaling than the middle manager autoscaling system because there's only one system that's responsible for it. So we don't have this case where we're autoscaling up and down in steps. And it's able to handle spikes a lot faster and also scale down to free up the capacity a lot faster. So that's compared to the middle manager system on the left. And another note is, since there are no middle managers at this point, we don't have any long-running pods anymore. So the longest a pod can run is however long a task can take to run. So in the first scenario that Sunit mentioned, if we have a surge of ingestion where we go from, say, 3 tasks running to 12, filling up both the nodes, and then these tasks exit, most of them, and we spawn a few new tasks. We'll initially have 2 nodes the same way as the autoscaler system will have 2 nodes, since you can't really control necessarily where the tasks are being placed. But eventually the task will exit out and the replacement will be assigned onto the next node and you can scale down the other node. So you basically are able to scale down your nodes a lot more consistently than with the middle managers because the pods run for a lot shorter. And since each pod is only responsible for running one task, there's no issue with idle spots on a middle manager. So a middle manager runs more than one task. So if you only are running, say, one task on a pod with 4 slots, then you're basically requesting more resources from Kubernetes than you need because you would be requesting resources to run 4 tasks and only be running one. So this is an example of some cost savings we saw by removing idle task locks, saving 25%, just due to the faster scale down and all the things I've talked about. All right, so a quick demo. This is just a local cluster with the Kubernetes task scheduler enabled. So I'm just going to show a pod coming up and what this looks like. So actually first I'm going to show, there's a middle manager running here, but it's not actually going to be running the task. And you normally don't actually need to run anything. So the task is submitted. And you can see there is a Kubernetes pod running here, doing the work. All right, so the task has succeeded and you can see the pod has cleaned itself up. So that's kind of like a very small scale version of the scale up, scale down that can happen. So a couple of tips for setting the system up. One thing I kind of glossed over earlier is around how to schedule pods onto nodes in Kubernetes. Since we're letting Kubernetes do more of the pod scheduling in the system, the way that the configuration you use is more important. So generally, you're going to want to schedule pods onto the most full nodes. So there's a standard strategy in Kubernetes to do this. And that's so you can do the node scaling down that I mentioned previously faster, because the newer tasks won't get scheduled onto that node. They'll get scheduled onto the one that already has tasks scheduled onto it. The second thing is around container startup time. So since we're spinning up a new pod for each task, this tends to mean that the average case and the worst case scenario startup time is a lot better than with middle managers, but the sort of 0 to 10th percentile or the best case scenarios are slightly worse because you always have a little bit of overhead to spin up a container. So a couple of things we discovered to sort of like make the container startup faster. One is these local ephemeral disks. So use something like an empty dir in Kubernetes to spawn your scratch space for the peons rather than attaching a volume or something like that, just because that volume attachment process ends up taking a decent amount of time and it slows down your task startup. And the other is if you have really high throughput streaming or very low lag requirements, it may be more reasonable to start the system with batch or compaction because a second or two is not going to be as much of an issue with those things. Although we have found that, say, for streaming, compared to the auto scaling system, the system actually works better at preventing lag during streaming handoff because the average pod spin up time is much lower. And the other thing is, since we no longer have like this second layer of waiting with the middle managers, the cold node startup time becomes more important because that's kind of the only thing you'll be waiting for. And it is helpful to use something like a Kubernetes over provisioner, which is basically a deployment that creates a bunch of pods that are evictable so that you have a little bit of warm capacity to schedule new ingestion pods on. And that is all.